Let's look at how shielding and increasing effective nuclear charge affect the reactivity of the alkali metals. As we move down the alkali metals, something important changes. Each element adds another energy level. That means the valence electron is farther from the nucleus, and there are more inner electrons in between. Those inner electrons create shielding. We can describe this mathematically using effective nuclear charge. In the equation shown on the screen, Z is the number of protons, so it's the atomic number, and S represents shielding. So effective nuclear charge, Zₑff, is the net pull felt by the outer electron. Notice what happens to the values for nuclear charge and shielding as you go down the group. Z increases from 3 to 55, but shielding increases dramatically, from about 2 to about 50. So even though the nucleus becomes more positive, most of that extra pull is cancelled by shielding from the core electrons. Notice, however, that the effective nuclear charge increases only slightly. Meanwhile, the distance separating the valence electron from the positive charge of the nucleus has increased so that the valence electron in cesium is roughly 2 to 3 times farther away from the nucleus than it is in lithium. Ionization energy, IE, is the amount of energy required to remove an electron from an atom or an ion. Ionization energy depends on two major factors: how strongly the nucleus pulls on the electron, which is determined by the effective nuclear charge, and how far away the electron is, given by the principal quantum number, n. As we go down the group, n increases from 2 to 6. And because the electron is farther away and heavily shielded, the ionization energy drops. Lower ionization energy means the electron is easier to remove. And that's why reactivity increases as you move down the alkali metals. It's not because the nucleus is weaker, but because the shielding and distance make the outer electron easier to lose. Reactivity isn't random. It's the balance between nuclear charge, shielding, and distance.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.